I'm including this example because I want you to see how to handle a third order differential equation using variation of parameters. We've got y triple prime plus 4y prime is equal to the secant of 2x. Thankfully, it's in standard form. We have m cubed plus 4m is equal to 0. That's going to give us that m is equal to 0 or plus or minus 2i, if I'm reading that correctly. So we'll say that y1 is equal to 1, right? E to the 0x. y2 is the cosine of 2x, and y3 is the sine of 2x. Our Wronskian is not a surprise. The first row is y1, y2, and y3. So 1 cosine of 2x and sine of 2x. And then remember, in the case of a 3 by 3 Wronskian, or a Wronskian with 3 functions, we have 3 rows, each of which is just a successively higher order derivative. So the first column is 1, 0, 0, those derivatives. The second column is cosine 2x, negative 2 sine 2x, and then negative 4 cosine 2x. The third, did I say row? These are columns. The third column is sine 2x, 2 cosine 2x, and then negative 4 sine 2x. And the way we compute this 3 by 3 determinant, I'm going to expand down the first column, taking advantage of those zeros. And so we have 1 times 8 sine squared of 2x plus 8 cosine squared of 2x. I think this whole thing is going to turn out to be 8. That's not really the interesting new or necessary part. W1. W1 is going to have its first column replaced by 0, and then 0, and then the secant of 2x. So it's like the W1 that we saw before, except we have 2 zeros before we write down f of x. The rest of the 3 by 3 determinant is the same as that for w. So I'm just going to duplicate that and bring it down here. And then in this case, I'm again going to expand down the first column. 0 and then 0 is not going to be very interesting. We're going to have here the secant of 2x times the determinant that we get when we cross out the row and column that contain the secant of 2x. And so we've got cosine 2x, sine 2x is the first row, negative 2 sine 2x, and then 2 cosine 2x is the second row. That looks to me like it's going to be 2 cosine squared 2x plus 2 sine squared 2x, with the result that this is 2 times the secant of 2x. W2, you can guess what it is. The middle column is 0, 0, secant of 2x. For W3, the third column is 0, 0, secant of 2x, with all remaining columns the same as what they are for W. In all these cases, we can take advantage of a bunch of zeros. W2 ultimately is going to become negative 2, and W3 is going to become negative 2 times the tangent of 2x. You've pretty much seen the point of me bringing this one in, but let's go ahead and finish it. U1 is going to be the integral of W1 over W dx. U2 and U3 are what you think they are, W2 over W dx integrated, and then the integral of W3 over W dx, respectively. Using the determinants that we found above, U1 is the integral of 1/4 secant of 2x dx. And so it's going to be, that's a secant of 2x, not secant squared. And so it's going to be 1/4 of the natural log of the absolute value of the secant of 2x plus the tangent of 2x. U2 is ultimately negative 1/4 x, and U3 is 1/8 natural log cosine of 2x. You might say, wait a minute, the integral of the tangent is the natural log of the secant. Yeah, there's this negative, and I applied that as an exponent. And then, again, this finishes as before. Y sub p is going to be u1 y1 plus u2 y2 plus u3 y3. Finally, our solution is going to be c1 plus c2 times the cosine of 2x plus c3 times the sine of 2x plus 1/8 times the natural log of the absolute value of the secant of 2x plus the tangent of 2x, because that one was u1 times a constant, well, u1 times 1, minus 1/4 x times the cosine of 2x, that's u2 y2, plus 1/8 sine of 2x times the natural log of the absolute value of the cosine of 2x, and that's u3 y3. And then if you were interested in identifying an interval of solution, we want one where these are all defined, but if we go to the original equation, the right-hand side, the input function, where is it, was the secant of 2x. And that's defined on an interval where 2x goes from negative pi over 2 to pi over 2. So here, I would give the interval from negative pi over 4 to pi over 4, not including pi over 4, and you'll find that that works for all of the denominators in these trig functions in our solution.